All right, welcome to our second module in the theories on the origins of life. We're going to be looking at stars and planets, and particularly in the life cycle of stars is what we're interested in. Before we get going, take a moment and have a think about what do you think a star is? Write down a little bit of a description as to what you think one is. See if you can identify the name of the nearest star to the planet Earth. How do you think stars actually are formed? Do you think stars ever die? And what other things can you see in the night sky other than stars? So pause the video and go through and answer those questions. We'll come back and I will give you an idea of some of the answers. All right, so we're going to, through this, talk in more detail about what a star is and exactly how they work, but a really simple sort of summary would be that they're a giant burning ball of gas held together by its own gravity. The name of the nearest star to the planet Earth is actually the Sun. Sometimes if you're being fancy and technical, you can call it Sol, S-O-L, but we just generally call it the Sun. So if you went looking in Google and found it was something like Alpha Centauri or something like that, you're like, it's actually not, the Sun is closer. Stars are formed through a process that we're going to go through a little bit later, so we'll come to that in a bit. And yes, stars do die, and we'll talk about what can happen when they die. And for number 5, we're going to also go through some of the objects other than stars you can see in the night sky, but to give you an idea, we're thinking things like asteroids and meteors and moons and things like that. So let's get started. So what is a star? A star is a ball of gas that is held together by its own gravity. Now that gas is sort of constantly burning. It's actually through a process of nuclear fusion. But what's happening is we have the gravity of all that gas, all that matter, all that mass is sort of constantly trying to cause the stars to collapse inwards. So it's almost collapsing in under its own weight. However, as that hot gas is going through nuclear fusion and all of that, it's actually creating sort of a pressure outwards. So you've got the gravity trying to cause it all to collapse inwards, but you've got this other pressure pushing back outwards. And it's actually, when they're in balance, that's how the star sort of maintains its shape and size. It's through something called hydrostatic support, that's the technical term, but basically the gravity is pushing inwards, is counteracted by pressure pushing outwards, and it holds itself sort of in stasis like that. So we're going to watch a video here on the life of a star, and then we're going to go through the different points in detail.
Way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter, and eventually the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out. And at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our Sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the Sun, this will be the beginning of the end.
What happens is, as the outer layers of the star get farther and farther from the middle, the force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang! The outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star billions of years ago, before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Alrighty, so our very first starting point for the life cycle of a star is as a protostar. So we'll have you can even go back slightly further to a stellar nebulae, and so stellar nebulae, it's just a big cloud of gas and dust, and eventually all that gas and dust, all those little particles, it doesn't matter how small they are, if something has mass, or is made up of matter and it has mass to it, it has gravity, no matter how small. You have gravity, you're made of mass, but your mass is just so much less than the Earth's that your gravity is also so much less than the Earth, so we don't tend to talk about our own gravity. But out in space, even tiny specks of gas and dust, even an atom, because it's got mass, it has gravity. And if you have enough of these things together, their gravity sort of starts to act together. And so they sort of start falling in and collapsing in towards each other under their own gravity. And they end up coming together to form this protostar. Proto means sort of beginning, or like a precursor to something. So this is sort of not quite a proper star yet, it's sort of the beginning star. And as we have all this gas and dust collapsing in under its own gravity, they create more and more pressure in the very middle. And that center, that very middle bit, under all this pressure gets hotter and it gets denser as more matter is packed into this protostar. Eventually, that pressure and that heat is going to get enough for nuclear fusion to actually start occurring. And that's where we would move to the next stage, which is a main sequence star. Alright, so what is a main sequence star? Well, it is actually the point at which stars spend most of their life. And so a star is a main sequence star when it has achieved stable hydrogen fusion at its core. So as it's a protostar, you've got all this gas and dust collapsing inwards, and maybe a little bit of hydrogen fusion occurs. But until that hydrogen fusion, where you have hydrogen atoms being combined with another hydrogen atom to form helium, until you're at a point where that is occurring in a stable manner and it's not stopping and starting, until it happens in a stable way, it's not a main sequence star. Once it gets to this point, you will find that the star will now remain stable for millions or maybe even billions of years, depending on its mass and how much fuel it has. Now, a little bit counterintuitively, the bigger the star is, the faster it actually uses its fuel. So the very biggest stars might only be a main sequence star for millions of years, whereas slightly smaller ones will be main sequence ones for billions of years, because the smaller ones don't burn through their fuel as quickly. Our sun is actually an example of a main sequence star, and main sequence stars have the main fuel source of hydrogen. A couple of fun facts, just to give you an idea of scale. The sun has approximately 100 times the radius of the Earth, so it's quite a lot bigger. And you can see sort of in the image, sort of to scale how big the Earth would be in comparison to the sun. In fact, if you had 1 million Earth-sized planets, you could fit them all in the sun. That's how big it is. So it is so much bigger than the Earth. It can be quite hard to get your head around it. All right. Eventually, a star's going to get to a point where it's used up all of its fuel, or of its hydrogen fuel source. And once it uses up its entire hydrogen supply, it doesn't stop burning. Rather, it just starts using a different fuel. In fact, it starts using helium, because as it's been doing hydrogen fusion, it's been making a lot of helium. All right, and so it's made all this helium, and it's now run out of hydrogen, so it turns to start using helium, and it does the same thing. It starts taking a helium atom and colliding it and combining it with another helium atom to make heavier elements. All right. When it starts doing this, it causes some changes in its structure and shape, and the star actually starts expanding. And if it's a smaller star, it will expand to becoming a giant star, but if it's a much bigger star, it'll expand and become a supergiant. At this point as well, we also see the star start to cool down. So it starts off much hotter, and then as it enters this phase, it cools down and becomes actually red. I mentioned in the previous video that the colour of a star is directly related to its temperature. So red is actually towards the cooler end of the spectrum. It's still very hot by our standards, but it's actually cool for a star. As you move on from here, what happens to the star next will depend on how big the star actually is. If you want an example of a star that's in this part of its life, you can look to Betelgeuse, which is a star in the Orion constellation. It's one you can actually see at night, and it has a bit of a reddy glow to it because it is a red giant itself. So that is what happens after main sequence. It becomes a red giant. Now, like I said before, what happens next to a star will depend entirely on its size. So the first thing you need to understand is the term called solar mass. So our sun weighs about 1.989 times 10 to the power of 30 kilograms. That's actually a very big number. That's 1989 and then like 27 zeros after it, kilograms. So instead of having to write that out, we just take that number and we say that that is one solar mass. So one solar mass is how much our sun weighs. All right. If you have 2 solar masses, that's 2 times the size of our sun. If you had 10 solar masses, it would be 10 times the size of our sun. If you had 0.5 solar masses, that would be 0.5 times the size of our sun, so half the size of our sun. So we're just going to talk in terms of solar masses for the next little bit, so you just need to understand what that term means. So we've got our red giant, or a red supergiant. If it is less than 8 solar masses, so less than 8 times the size of our sun, so that could be our sun would fit into this category. Something 2 solar masses, 3 solar masses, they would all fit into this category as well. Stars of this size, when they run out of fuel as red giants, they then start to shed their excess mass in something called a planetary nebulae. All right, so that's what these pictures on the screen are. So we have the outer layers start to expand and to leave. So if you remember with red giants, as that phase starts, they also start to expand. And once they start to get to the end of that, those outer layers keep expanding outwards. Once this has happened, you're left with at the very center of this planetary nebula, you've got the outer layers have all shed and spread out further, but the very core remains, and that core that remains is called a white dwarf star. Now, white dwarf star normally is about the same size as the Earth, but has the same mass as the Sun. So that second dot point might be a little bit confusing. It says a typical white dwarf is about as massive as the Sun, yet only slightly bigger than the Earth. What that means by saying massive there is it's talking about the actual physical mass, how much it would essentially weigh. And so it would have the same amount of mass or matter as the Sun does, but it's packed into space, into physical space, about the same amount as what the Earth takes up. So if you think about having the Sun and you squished that down to the size of the Earth, that's what a white dwarf star is like. So it's actually one of the densest forms of matter. The only thing we think that is more dense than a white dwarf star is what's called a neutron star. Now, eventually a white dwarf star will use up all the remaining fuel it has. At this point, it's sort of really grasping at those last few lighter elements, and eventually it's going to use them up. And when it does, it becomes a carbon black dwarf star, because really all that's left is carbon, and it's not using that in any type of fusion, and carbon at this point is black. So that's why it's a carbon black dwarf star. Now, that was what happens to stars that are less than 8 solar masses. However, if you have a star that is more than 8 solar masses, so 8 times the size of our Sun or bigger, those are the stars that are going to become supernova. And supernovas happen because instead of the outer layers spreading off like it would happen in a planetary nebulae, they actually collapse inwards. So in these very, very big stars, their outer layers at this point start to move inwards. And as those outer layers move inwards, the core starts to rapidly move outwards. So you've got the outer layers coming in and the inner layers moving out, and eventually those two layers meet. And when they meet and they collide, that's where you have a supernova explosion forming. Again, after that, what happens also depends on what is left and how big that is. The pictures on this slide, you'll notice there's some arrows. The arrows are pointing to regions of space, either before a supernova or after the supernova has occurred. Supernovas let off massive, massive amounts of energy. And so what can happen is the amount of light that gets let off from that can suddenly mean you might not have ever been able to see that star. And when it goes supernova, suddenly there's a big flash of light in that space, and it might be the brightest thing in that part of the sky, completely outshining things. So in the first images, you've got on the left here, there's sort of nothing in that region of space where the arrow is pointing to. And then after the supernova, there's this very bright light star, what looks like a very bright star in the night sky, but that's actually a star that's gone supernova. That's why it's emitting that much light. You couldn't actually see it beforehand. In the sort of more redder image up the top, it's pointing to a star that you can't really see, but as soon as that explodes, it becomes the brightest thing in that image by a long shot. So that's a couple of examples of when stars go supernova. So we've had our very, very big star go supernova, and there's a little bit remaining after that. Now, if what is less is on the smaller side, and it is less than 3 solar masses, then that remaining stuff becomes a neutron star. Now, neutron stars are very small. They're only like 30 kilometers across, but they're very, very dense and very, very hot. To give you an idea of how dense they are, if you had a sugar cube sized amount of a neutron star, so it's like 1 centimeter cubed, if you had just that much of a neutron star, it would weigh more than 1 billion tons. So a sugar cube sized amount of a neutron star would weigh more than 1 billion tons. So just let that sink in for a moment. That's just how incredibly heavy and how dense that is. If you hear the word pulsar, a pulsar is just a type of neutron star. So it's not a completely different thing, it's just a category of neutron star. On the other hand, for the most biggest stars out there, the ones that were big enough to go supernova, and they're big enough that what's left is more than 3 solar masses. These are the stars, and the very few, very rare ones that will become a black hole. And black holes aren't actually holes, it's a bit misleading. It's a point of intense gravity. It's where so much stuff is packed into such a small space. There's so much matter there. And it has such gravitational attraction that even light can't escape the gravity. And light will be either bent around it, or at a certain point, any light shining at this black hole will be unable to bounce off it and to escape. And that's why they appear black. It's because there's no light that's being able to be reflected off them, because they absorb the light and don't let it bounce and reflect back off it, because their gravity is so strong it's actually able to have an effect on the light. It is thought that black holes are actually what is at the center of most galaxies. They're able to hold. That's why they're able to hold things like all these stars and their own systems in orbit around them. So that's sort of the thinking that we think that might be black holes at the centers of galaxies. All right, so see if you can match the label to the diagram. The very first one gets 2 labels. So the one that's labeled A and 1 here has 2 things. You have to, it's one word over here is both A and number 1. And see if you can work out the labels that go for A, B, C, D, and E, and also for 1, 2, 3, 4, 5, and 6. You might find it easier to go backwards at certain points, or to go, okay, well, this must be this thing because this is happening, and therefore the one before it must be this. So pause the video and go and fill that in, and then we'll come back and we will do it together. All right, so if we start off with A and 1, that's right back at the start, which means this is back where we're talking like protostars and stellar nebula. So if we look at our list, we have stellar nebula here. So that would be A/1 for that first one. And then we'll go down the letter pathway. So we go from A to B. If we look right through here, we'll see that there's no point at which it could split and become either a neutron star or a black hole. So this tells me that this is going to be the pathway for smaller stars. So after we have a stellar nebula and our protostar sort of point, we move into main sequence stars. So B is going to be a main sequence star, and because it's on the smaller side, it would probably be the same mass as the sun. So B is a main sequence star that's similar size to the sun. And then we'll go on from that. After main sequence is red giant or supergiant. Again, it's on the smaller side, so this will just be a red giant. So C is a red giant. And then from that, we go to a planetary nebula as those outer layers start to shed. So D would be the planetary nebula. And finally, E would be our white dwarf star. All right. So there we have them. Just excuse the handwriting, it's a little tricky to write them here. On the other hand, if we go down our number pathway, so we go from 1, which was our stellar nebula, to 2, which is again, it's going to be main sequence, but this is a much bigger main sequence star. If you look further down the pathway, you can see there's going to be a split that looks like it's probably going to be the split where it could be a neutron star or a black hole. So that tells me that this is a bigger pathway. Sorry, the pathway for a bigger star. So 2 is going to be our main sequence star, 10 times the mass of the sun. All right, and then we move on to 3. 3 again, red gianty sort of phase, but this is a really big one, so it's going to be a red supergiant. Ooh, a bit of a funky looking 3 in there. And then we're going to get to 4. After a red supergiant, we would have a star. This is where a star would go supernova. So 4 is our supernova. And then if we go 5, 5 is what a neutron star looks like. So and that's because you can sort of see with 6 there's actually a black dot in the middle, which would be a black hole. So neutron star is number 5 and black hole is number 6. Oops. It's a bit funky looking. That looks more like a G than a 6, unfortunately. Let's try that again. There we go, 6. So supernova 4, black hole 6, stellar nebula A/1, red supergiant 3, white dwarf E, planetary nebula D, neutron star 5, main sequence star approximately same as our sun B. Main sequence star, 10 times the mass of our sun, 2. And red giant is a C. So those would be the answers for that. So here we have a way you can sort of summarize all that. So molecular cloud, aka stellar nebula, right at the start there, then it becomes a protostar, then a main sequence star, then a red giant or red supergiant, depending on how big it is. Smaller stars become planetary nebulae on the left there, and then white dwarfs, whereas bigger stars go to the path on the right. So they go supernova, and then depending on how much they leave behind, either a neutron star or a black hole. One thing we do like to know about stars is how bright stars actually are. When we look out into the sky during the day, there's only one star we can see, and that's the sun, because it's so close to us. It doesn't matter if it's actually not that bright. It's so close it appears it's really bright to us. So we actually have to have two different ways of measuring brightness. That is through apparent magnitude, which is how bright a star appears to us on Earth. So the closer a star is, the brighter it's going to appear to be. It doesn't mean it's actually a bright star. It just appears bright because it's closer. The other type of brightness is called absolute magnitude, and that's the actual brightness. It's absolute brightness that a star has, and this has no connection to distance. It doesn't matter how close or how far away it is. That's how bright the star actually is. So apparent is how bright the star appears to us, and absolute brightness is how bright it appears to us. Now, we represent this on a scale, and there's a couple of points to know about reading the scale. The first is that each level difference is 2.5 times difference in brightness. So from 1 to 2, it's not just like double as bright, it's 2.5 times as bright. So it's a bit more than that. And the other thing is, and this is where things get a little bit confusing, the more negative the number that you have, the brighter that actually means. So the more negative a number, the brighter that star actually is, and the more positive, the dimmer it is. So this number scale down the bottom is quite handy. So the red left side where we have negative numbers, as they get more and more negative, that's actually saying it's getting brighter and brighter. On the other hand, on this sort of purple side on the right, as we get more and more positive and that positive number gets bigger, we're actually talking about a fainter or a dimmer star as it gets more and more positive. So here in our table, if we look at the sun, for example, the sun has an apparent magnitude. So this is how bright it appears to us. It has a really negative apparent magnitude, which means it appears really bright to us, negative 27. So it appears really bright. But if you look at how bright the sun actually is, it's actually on the positive side of the spectrum. Its actual brightness is pretty low. It's on the pretty dim side of the spectrum. On the other hand, if you have a star like Betelgeuse, it appears to be pretty faint to us. Like, you can actually see this in the night sky, but it doesn't appear to be very bright. It's in fact, it's on the positive side, but its actual brightness is on the negative side, which means it's actually a lot brighter than that. So that's what its absolute magnitude is, and its actual brightness is. So a couple of things there when you're reading that scale. Just really remember, negative equals brighter. All right. And so apparent magnitude is how bright it appears, and absolute is how bright it actually is. One way we often can show this sort of relationship between brightness and temperature of stars, because there is a big connection, is using something called the Hertzsprung-Russell diagram. It's also just called the HR diagram, which you're fine to call it that as well. And so it's a graph that shows the relationship between brightness and temperature of stars. And a couple of things to note about this. It's absolute magnitude, so it's talking about the actual brightness of stars. And that's on our y-axis here. And so the very furthest point away from the start, this is really bright stars up the top here, and much dimmer stars down the bottom. Along the bottom here, along our x-axis, is surface temperature. It's measured in degrees Kelvin, which is a little bit different from degrees Celsius. But think of it this way, whatever you have in degrees Celsius, if you add 273 onto that, you've got the equivalent temperature in Kelvin. So it's a pretty easy conversion, so don't stress about that. And for what the numbers we're looking at here, it's almost worth saying it's just the same as Kelvin, Celsius, sorry. But across the bottom, it doesn't go from low to high temperature. It actually goes from high to low. So anything up in this top corner here, they're very bright stars with very hot temperatures. And over the other side here, if you're down the bottom corner here where my mouse is now, these are dim stars with very low temperatures. And what scientists have seen is that there's a connection between particularly for main sequence stars, between temperature and brightness. So the hotter a star is, the brighter it is, and the cooler a star, the dimmer it is. So most stars are brighter. Most stars are brighter when they are hotter. Okay, so hot stars equal, the hotter a star is, the brighter it is. Now, the two sort of main exceptions here are supergiants and giants over here. These are bright stars, even though they're kind of cool. And the other one is white dwarf stars, and they're quite hot, but they're not very bright. And the reasoning here is mainly, I would suggest, because of their size. Supergiants and giants tend to be very big, so even though they're not very hot, because there's just a lot of them, they end up appearing a lot brighter, whereas white dwarf stars tend to be quite small. So even though they're quite hot, there's just not much of them to give light off, so they tend to appear dimmer. Alright. Another thing to keep in mind when looking at things out in space is something called parallax. And parallax is this idea that things can seem to move, not because they're actually moving, but because the person or thing looking at them is actually moving. One way of thinking about this is if you're in the car, you see things passing you in the car. It's not because those things are moving, it's because you're moving. Generally, though, with parallax, you're talking about a situation where you aren't aware that you're moving. In a car, you tend to be pretty aware that you're moving. But if you think about how we're moving on the Earth, we don't feel that movement. And so if we look at stars in the night sky, it can look like those stars might be moving through the night sky, but what's actually happening is the Earth's position and rotation is changing, and it's our movement that's becoming different. And so that's why things look like they're moving to us. So parallax is the apparent movement of objects at different distances due to the movement of the observer. Now, one thing I didn't emphasize just before was the different distances. This is just the idea that the closer something is, the more it might look like it moves as compared to something even further away. So really simple way of thinking about this is if you are in the car, trees near the car seem to be moving quicker than the mountain in the distance, because that mountain is further away. It's you have to move a lot more before it looks like it moves as much. All right, so that's just what it means by different distances. Other things that sort of are the result of parallax is why the sun looks like it moves through the sky, even though we're the ones moving. That's a parallax thing. We're not aware of the Earth, our movement on the Earth. So when the sun seems to move through the sky, we think, oh, the sun's moving. Well, no, the sun's actually not moving. It's us and the Earth's rotation that's happening there. Constellations can seem to be in different places in the night sky throughout the year, not because those stars are necessarily moving. They might be moving away from us, but that movement throughout the year is actually due to our movement around our sun and our different positions in our orbit around the sun throughout the year. One thing you can actually do to sort of see this is if you hold a finger out at arm's length from your face, close one eye and then try and switch in which eye is open and go back and forwards. And what you should see is, because the eye you're looking through changes and it's slightly offset from the other eye, that your finger should seem to almost jump backwards and forwards in front of you. And it might look like it's moving, even though you would know it's not. And that's just because the position you're observing from, even just by changing your eyes, that position's changing, making it look like the thing you're looking at is changing, even though it isn't. So this brings us to just a bit of a discussion on some of the other things we might see out in the night sky. So to start us off, planets and moons. So we've sort of maybe mentioned them, or we sort of have heard these terms, but we don't necessarily always know what makes a planet, or why something can be classified as that. Basically, a planet is a sort of a rocky structure that orbits the sun, or it could be a star in a different solar system. It has to have sufficient mass that it is round or nearly round, and it also can't be a satellite or a moon of another object. Okay, it has to orbit the star directly. It can't orbit something else that then orbits the star. And it also has to have been able to remove debris and small objects from the area around its orbit. Basically, it has to be of a certain size, is sort of where we draw the line at a planet. Moons, on the other hand, moons are rocky sort of structures, I suppose, that they don't orbit a star directly. They orbit something else. They orbit a planet, basically, that then orbits a star. So these are celestial bodies that make orbits around a planet. We have one moon. Not all planets have one moon. Some of them have much more. Jupiter has 67, Saturn has 62, Neptune has 13. So it's quite interesting looking at how many different moons different planets have. Next thing is nebulae. We've sort of mentioned this already. We have a bit of an idea. We can have planetary nebulae, which are part of the life cycle of the star towards the end of smaller stars, or we could have stellar nebulae, which is sort of right back at the start of the life cycle of the star. But generally speaking, they're always clouds of gas and dust. They're found within galaxies, and so you have a few different kinds. The picture here is of one set of nebulae called the Pillars of Creation. It's quite a famous looking one. And you can go and look it up and you'll get pictures like this. But even though they might occur for different reasons and be in different points in the life cycle of stars, they are made up of the same things, and there's something else that we sometimes can observe, not necessarily with the naked eye, but definitely through things like telescopes and the like. The next thing we might think of being able to see in the night sky would be constellations. Now, constellations are not an actual structure, rather they're groups of stars that we view as forming a pattern. So it's kind of like we as people have looked up at the night sky and played connect the dots with the stars that we see, and we've come up with images that they make. And a lot of the time the constellations that we talk about, and most people would know of, particularly with things like astrology and that sort of thing, which is not a real science, but those sorts of things, those constellations are sort of more Western zodiac and or constellations and that sort of thing, and not all cultures in the world actually have the same constellations. They might look up at the same stars and see very different patterns, and that's because these aren't actual structures. They're just human imaginings and patterns that we've put on and played connect the dots with the different stars in the night sky. The next thing out there in space is galaxies, and galaxies are systems of millions or billions of stars, and they're all being held together by gravity. You hopefully know that we live in the Milky Way galaxy. It's a spiral galaxy. You can sort of see a stylized picture of it down the bottom on the left there. Specifically, our solar system is found in what's called the Orion Arm, and we're orbiting the center of this galaxy, which we think there might be a black hole at the very center causing us to orbit. We're orbiting the center of the galaxy at about a speed of like 200 kilometers per second, so it's quite quick. And so galaxies, just all these different stars and all these different solar systems and sorts of things rotating around a center point. And some of the next things we have are comets, meteors, and asteroids. Sometimes these words get used interchangeably, but they're not actually the same thing. So a comet is an object that's moving in space. It is made up of a core of ice and dust, and as it gets near the sun, that ice starts to vaporize from the heat and forms sort of a vapor trail behind it, which is its tail. So comets specifically have a core of ice and dust. That's quite a defining feature about them. Meteors are matter from outer space. They enter the Earth's atmosphere. They burn up on re-entry. As they burn up on re-entry, you can get water shooting stars. That's just a bit of meteor burning up as it enters the Earth. Generally speaking, whatever's falling, whatever meteor you have will completely burn up, and only occasionally does anything actually land on the ground. And if it does, it tends to be pretty small anyway. Finally, we have asteroids, and these are small rocky bodies that orbit the sun, so similar to meteors, but they're not falling through the Earth's atmosphere. They're actually really small. They're not big enough to be a planet or have any of the other characteristics, and they don't orbit a planet themselves, so they're not a moon, but rather they're small rocky bits that actually orbit the sun. And so that's what an asteroid is. Final sort of thing out there in space is something called a quasar. Quasars, as we understand them, are the most distant objects in the universe. And we think that quasars are formed when you've got a black hole and it's at the very center of a galaxy, and instead of having all those stars and all that gas and dust orbiting this black hole properly and having a stable galaxy, what happens is it starts to pull in the stuff that's orbiting it. They're not on the right sort of path to just stay in a perfect orbit around it, and they start getting pulled in. And as this happens, and it's almost like that black hole starts eating it up, it actually ends up releasing a massive amount of energy, creating a quasar. And so that's what we think quasars actually are. All right, this brings us to the end of this module. Thank you so much for sticking with me. Remember, if there's anything you didn't understand, you're able to go back and rewatch bits of it. You can speed things up, slow them down, or go back through it as you need to. If there's anything you still need help with, just remember to ask your teacher. They're more than happy to help. Anyway, that's it for now, and I'll see you in the next video.